Today we are going to discuss reaction mechanisms which are composed of elementary steps. What do we mean by an elementary step? Well, it is a sequence of the steps that a reaction might take to lead to product formation. Imagine, for example, we have the reaction before us here. And we might assume right off the bat that NO simply somehow collides with O2 and we get our product. This, however, turns out to be not true. And the first clue to this being not true was that N2O2 was detected in the course of this reaction, meaning that something else must have been happening. This led to the proposal that an initial elementary step could be the collision of two NO molecules to form N2O2, which in turn provides a reactant for the second elementary step where N2O2 collides with O2 to form the product. Something interesting is happening here. N2 is formed in step 1, consumed in step 2, and therefore does not appear, as expected, in the overall reaction. Another way of visualizing this is to just look at the molecules themselves and imagine how they collide, how bonds are broken or how bonds are formed to lead first to our molecule in step 1, which in turn goes on in step 2 to form the final product. Reaction intermediates are what we call the compounds that appear in one elementary step and are consumed in a second elementary step. This means, again, as we've already noted, that the intermediate won't appear in the overall equation, and yet it has a very important role to play in the progress of the reaction. Each elementary step has something we call a molecularity. And by definition, molecularity means the number of molecules that are reacting in any given elementary step. Unimolecular is one possibility. A reaction has only one reactant molecule. Bimolecular, up next, is an elementary step with two reactant molecules. And, as you might guess, termolecular is an elementary step with three reactant molecules. Much easier to understand this if we look at a visualization. In this case, step 1 here, or category 1, I should say, is a unimolecular reaction. A reactant, only one, forms product. If we move on down to bimolecular reaction, we see there's two different possibilities. One is two A molecules come together to form our product, and an alternative is A plus B come together to form our product. Finally, for termolecular, in other words, three reactants, more possibilities arise. And there's a couple listed here, but others could be possible as well. The thing that we want to understand about the elementary steps of a mechanism is that one of them is always going to be rate determining. And the rate determining step is going to be the slowest step in the sequence of elementary steps. This, as you can imagine, has important implications for the rate law itself, because the slowest step is going to be rate determining overall for the reaction. And in turn, this slowest elementary step will allow us to write a rate law. Here are some examples of how to write a rate law for different types of elementary steps, meaning their molecularity. For a unimolecular reaction, we simply write the rate law as a function of the concentration of A. We write rate equals K times the concentration of A. If it's bimolecular, we simply write the rate law as a function of A and B. In other words, rate equals K times the concentration of A times the concentration of B. And for the other bimolecular scenario where two A molecules collide, we simply write the rate law as rate equals K times A raised to the second power. Now you might be saying to yourself, how can we write a rate law from an elementary step? We have learned all along that the only way we can get our exponents, i.e. first order or second order, is to do experiments and to analyze the data in order to determine the exponent. Well, just think of elementary steps and experimentally determined rate laws as going hand in hand, which we will elaborate on when we look at a practice problem. There are a sequence of steps in arriving at a reaction mechanism. We do need a rate law that is developed from experimental data, meaning a rate law for the overall reaction would be a logical first step. This allows, as we've already seen, for the formulation of a rate law depending on how the concentration of a given reactant impacts the rate of the reaction. Then having this in hand, it can help us to postulate a reasonable reaction mechanism and to propose which of our elementary steps might be rate determining. The rate determining step should predict the same rate as the rate law that is determined experimentally. They are two different things, and yet in the end, they must be the same. And as we have previously noted, the sum of the elementary steps must give the overall balanced equation for the reaction. All of this is easier to understand with an example problem. We're going to look at the gas phase decomposition of nitrous oxide, which is believed, emphasis on believed, to occur via two elementary steps. What are those steps? By the way, this is a little different from the reaction we're looking at before. This is decomposition, right? So a proposed step 1 is N2O decomposing to N2 and O. In turn, N2O, still a reactant, reacts with O to form N2 and O2. What are we going to do with these proposed elementary steps? Well, as noted previously, we need some experimental data that has given us a rate law for the overall, the net reaction. And that turns out to be rate equals K times the concentration of N2O. Now our job is to take these elementary steps and write an equation for the overall reaction. Following that, we will sum the elementary steps and identify the intermediate. And then finally, we'll use the experimentally developed rate law, in other words, the rate law that we see before us here, and find out which of the elementary step rate laws matches the experimentally determined rate law, and that will allow us to conclude which of these two steps is likely to be rate determining. Step A. We simply add our two equations together. We find that O cancels out, and this is our overall equation for the decomposition reaction. Clearly, the monoatomic oxygen atom is our intermediate, since it's the one that cancels out in summing the reaction. Finally, we will write a rate law for each of these elementary steps. Only the first one here, represented by K1 as this particular rate constant, matches the experimentally determined rate law. We certainly could write a rate law for step 2, but it's not going to be the same as what we determined from experiment. Therefore, this is the one that aligns with what we have learned from our experimental data. And that is really the name of the game for these reaction mechanisms, elementary steps, and development of a consistent rate law.